When a wave strikes a barrier or boundary between two different materials, some of the energy is absorbed, some transmitted, meaning it passes through, and some is reflected, meaning that it bounces off the other medium. The shape of the reflected wave varies as a result of the type of boundary. For example, say we have a rope with a loop on one end, and the loop is passed over a pole so that when a wave is produced in the rope, the loop is allowed to move up or down along the pole. We call this a free end. A single pulse is sent toward the pole, and when the pulse reaches the pole, the rope is able to slide up the pole. But the end is not totally absorbed by the pole. Some will be reflected back, and it's reflected back upright, just like the original pulse, just heading in the opposite direction through the rope. If we now consider the example where the rope is attached to a wall, the rope will not be able to move up and down on the wall. This is considered a fixed end. A single pulse sent down the rope toward the wall. When the pulse reaches the wall, the rope wants to move up and applies an upward force on the wall, but because the wall doesn't move, it in turn pushes back on the rope with a force equal and opposite, due to Newton's third law of action-reaction. Because the wall applies an equal and opposite force onto the rope, the reflected pulse is inverted or upside down, heads back through the rope. So if a wave strikes a heavy, harder to move material, the reflected wave will be inverted, where reflection can be applied specifically to light waves as well. We illustrate light waves as rays, and we can analyze the behavior of these light rays using ray diagrams. To begin a ray diagram, we must have a surface or boundary between two materials. It is also important to understand the concept of normal line. As you may recall, the term normal means perpendicular. So the normal line is a line perpendicular to our boundary or surface. If a light ray were to strike the boundary exactly along the normal line, then that light ray would reflect off the boundary and head back along the normal line in the direction from which it came. However, say we have light that is incident on the boundary such that it makes an angle with the normal line. We would call this ray that comes in the incident ray, and we can label the angle that this ray makes with the normal the angle of incidence. This angle cannot be measured from the boundary. All angles must be measured from the normal line. When light strikes the boundary, it's reflected off the surface as shown, also at an angle. We call this ray the reflected ray. It turns out that in all cases, no matter the kind of light or kind of boundary, the angle of incidence will always be equal to the angle of reflection. This is known as the law of reflection. Reflection is a very practical type of wave behavior because we wouldn't have the ability to see objects if it weren't for reflected light, unless, of course, the objects were luminous, meaning producing their own light. In a dark room, objects appear black because light is not present to reflect off those objects and enter our eyes. However, if light is present, light strikes all objects and reflects off those objects into our eyes. These objects are said to be illuminated, and thus we see. All reflected light that will still obey the law of reflection. A mirror is a thin sheet of glass that has been silvered on the back side. Light can pass through the glass, but strikes the silver and reflects off because it's unable to pass through. When we look into a mirror, the image that is produced looks exactly the same, hence the term mirror image. An image is produced because rays that reflect off your body travel parallel to each other toward the mirror. When the parallel rays strike the mirror, because it's a very, very smooth surface, the reflected rays all emerge from the mirror parallel to each other. Each of these rays obey the law of reflection, and because they emerge parallel, an image is produced that has the same size and shape as the object. This is known as regular or smooth reflection. All rays that enter are parallel, all rays that emerge are parallel, because the normal line is the exact same orientation on a smooth surface. An image will be produced, and that image will have the same size, shape, and other characteristics. There are some other interesting characteristics to understand about light that reflects from a flat or plane mirror. Imagine a little man standing in front of a mirror, and you're viewing the mirror. We will consider only those light rays that leave the person's right side and left side. And imagine that that person is raising their right hand. You can see the little hand next to the right arrow. There are normal lines, and light from both the left and right sides of the person will strike the mirror at the angle with the normal, and due to the law of reflection, will emerge from the mirror such that the angle of incidence is equal to the angle of reflection, and that light will enter your eye. However, our brains do not have the ability to detect the reflection of waves, the changing in direction of these waves. And instead, we perceive light traveling in straight lines. So if we trace those rays that head into our eyes back, we see that the image that is produced is considered behind the mirror. The characteristics of an image created by a plane mirror are interesting. The image that is produced will be the same size as the actual object. The image is not magnified or reduced in size. Also, the distance from the mirror to the image, di, is equal to the distance from the mirror to the object, do. So actually, we perceive that the image is twice as far away from us as the mirror. The image is also upright, not inverted or upside down, but you may have noticed, once you understood left and right as a child, that there is in fact a left-right reversal. You lift your right hand, and the image appears to be lifting its opposite hand. This, again, is due to our brain's inability to detect changes in direction of light rays, and its actual perception that light travels in straight lines. So when the little man raises his right hand, the light from his right hand reflects off the mirror and into our eye. And if we follow that ray back behind the mirror, we see that the right hand image is now located here. It is still the right hand of the object, but because of its position relative to us, it looks like the left hand. Imagine there were no mirror. If the little man was facing us, and there were no between you and that man, and he raised his hand that is on our right, it would be considered his left hand. So our brains use prior experience to confuse us into thinking it is the left hand that is raised, when in reality, it is actually his right. Finally, the image is considered a virtual image because it appears to be coming from behind the mirror. Virtual images are not created by actual light rays. So when light strikes a mirror and bounces off, our brains perceive that that light travels in a straight line and is actually passing through and behind the mirror. However, we know that the object is not actually located there. The image only seems to be there. If we were to place a piece of paper or a screen behind the mirror where the object appears to be, the image will not be projected onto a screen because light doesn't actually pass behind the mirror and wouldn't hit the screen. In comparison to a virtual image, there is also something called a real image. And this is an image that is actually made from real light rays. When light strikes a certain kind of mirror, it bounces off, and those light rays actually produce an image that if you projected that image onto a screen, it would be visible. We'll see a little bit more about that later. Also, a real image will always be inverted, unlike virtual, which could be inverted or upright. Here is another look at virtual images. The chess piece is actually in front of the mirror. Light from the chess piece strikes the mirror and enters an observer's eye. However, because the human brain cannot detect such changes in direction of light, we perceive that the light is coming from the chess piece that is behind the mirror. Because no light actually passes through and behind it, we consider this a virtual image. How large does a mirror have to be in order to see a reflection of one's entire body? Millions of light rays strike your body and reflect off in all directions. But let's just discuss those rays that leave the top of the object and reflect off the mirror and enter your eye, and those rays that leave the bottom of the object, reflect off the mirror, and enter your eye. The light that leaves the top of the object heads toward the mirror and follows the law of reflection as the light bounces off the mirror into your eye. Light that leaves the bottom of the object heads toward the mirror, follows the law of reflection, and travels into your eye. Because of the law of reflection, the mirror only needs to be half as tall as the person. Have you ever wondered why you stare at a piece of paper and you don't see your reflection, but when you look into a mirror, you do? A common misconception is that we don't see our reflection in a piece of paper because the light rays aren't reflecting off. However, if that were the case, then the paper would appear black, meaning all light that strikes the paper would be absorbed. Reflection of light is actually still taking place and is still following the law of reflection. But because at the microscopic level, a piece of paper is relatively rough, parallel rays that strike the paper reflect off non-parallel in a random fashion, and thus no image can be produced. This is known as diffuse reflection. We can see all the parallel rays striking the rough surface, and because they all still follow the law of reflection, and each normal line is oriented a little bit differently, then the reflected rays reflect off randomly and in all directions. We see that the light rays are non-parallel when they emerge from the surface, and therefore no image is produced. So light that hits a piece of paper is still reflected off into our eyes, but it's reflected off in all directions, so our brain cannot produce a clear image.